Strange but useful integral representation of Clausen integral function. I guess by now you know about Clausen integral function, that CL2 of theta function, which is defined as the sum from n equals to 1 to infinity of sine n theta by n square. I guess you know what is function now after we have done a lot of these videos. This also has an integral representation, which is very nice. In a CL2 of theta is defined as integral from 0 to theta of minus ln of sine x by 2 dx. So this is the integral representation, but here I'm trying to give you a new integral representation. Let's say second integral representation for Clausen integral function. So I'm just going to verify it, because I don't really know how someone can derive such formulas. Maybe it might not be too hard, but for now, let us just try to convince ourselves that this formula is true. And so for that, I'm just going to start from the right hand side and get the Clausen integral function. So let's do that. Now to do this, something that seems to make this simple is to change the cos theta in terms of e. So let's do that. Minus sine theta, and then integral from 0 to 1 log x of x square minus, this is 2 cos theta, so this is e to the power I theta plus e to the power minus I theta x plus 1. Yes, you know this formula. This formula comes from the I guess that's Euler identity or some formula, I don't know. E to the power I theta is cos theta plus I sin theta. From that formula we get this. Now we can actually factorize this. Yes. Okay, so over here we have x square minus e to the power I theta x minus e to the power minus I theta x plus 1. So I can take x common from the first expression. So I get x minus e to the power I theta. Yes, and if I take plus e to the sorry, this sign will actually become minus if I open the braces. So again, minus e to the power minus I theta, and that will be x minus e to the power I theta. Yes, and then d theta over here. Sorry, this is dx actually. Dx. Okay, next is we'll try to write this factorized form in terms of partial fractions. Minus sine theta, integral from 0 to 1 log x of x minus e to the power I theta x minus e to the power minus I theta. Okay, looks good. Yes. Now next step is to do the partial fractions, which you can easily do using the cover-up rule. So using cover-up rule, if I do the partial fractions, I get the following: 0 to 1 log x. Now while finding the coefficient for x minus e to the power I theta, I will just substitute e to the power I theta everywhere except this one. So I'm just ignoring log x for now because we are just doing partial fraction for this expression. So we will have e to the power minus I theta. Sorry. So except the expression other than this one, I will put e to the power I theta. So 1 by e to the power I theta minus e to the power minus I theta. Yes. And then plus x minus e to the power minus I theta. So I will put e to the power minus I theta in the other expressions. So 1 by e to the power minus I theta minus e to the power I theta. This is from cover-up rule, or you can simply go with the way of partial fraction that you know. It won't really matter. Now this is minus sine theta. Yes, I can also take this outside, e to the power I theta minus e to the power minus I theta, integral from 0 to 1 log x. And now this is 1 by x minus e to the power I theta, and minus 1 by x minus e to the power minus I theta d theta. This minus is because their order is changed over here. Okay, now for this one, now I can, to simplify this, now I can actually change this to geometric series. Let me do that. Minus sine theta, and I guess you know that this is also 2i sine theta. Yes, this is 2i sine theta. Integral from 0 to 1 and then log x. Now I can to form geometric series, first of all ratio should be less than 1. So for that, what I can do is multiplying by e to the power minus I theta, I get x minus 1, x e to the power minus I theta minus 1. Yes. Let me actually reverse this by taking minus sign. So minus of e to the power I theta, and then 1 minus x e to the power minus I theta. Similarly over here, that will be plus sign, and e to the power I theta, yes, by, and then 1 minus e to the power I theta times x dx. Very good. Now next step is sin theta cancels over here, and this is as I square, so that will be I by 2 integral from 0 to 1 log x. Yeah. Now this is sum from n equals to 0 to infinity e to the power I theta. Okay, let me write this first, e to the power I theta. Now please know that the modulus of e to the power I theta is always 1. So since x is going from 0 to 1, x is less than 1, so that's why the ratio is less than 1, so you can use geometric series formula. Now this is e to the power I n theta times x to the power n. Yes. Now over here it is also e to the power minus I theta. This is the first term. The ratio is this. So x to the power n times e to the power minus I n theta. Now we can interchange the sum in the integral. Yes. So we get I by 2, and the sum from n equals to 0 to infinity. Yes. And then integral from 0 to 1, we have log x. Yes. And now this is just x to the power n and e to the power I theta times n plus 1. Yes. Minus, this is also this will also have log x, this will also have x to the power n, and then this is e to the power minus I theta times n plus 1, okay, dx. Now please know that I can actually take log x to the power n common, and we will have e to the power I theta n plus 1 minus e to the power minus I theta n plus 1, and we know that if I that is just, you know that if I take that common, the remaining thing, this minus this, will just be again same 2i sine of n plus 1 theta. Yes. And the remaining is integral from 0 to 1 of x to the power n times log x dx. Now if log x has power 1, now this can be solved using the formula of gamma function. 2 to cancel out, so we have sum from n equals to 0 to infinity. This is just minus sine of n plus 1 theta. Yes. Now this is actually an standard formula. Integral from 0 to 1 of x to the power m ln x to the power n dx. If you have this integral, the answer is actually minus 1 to the power n gamma of n plus 1 by m plus 1 to the power n plus 1. Yes. Using this gamma formula, we can find its answer. So that will be minus 1 to the power 1 gamma of 2 by n plus 1 square. Yes. Now with this formula, we are really close to the solution. Now this is sum from n equals to 0 to infinity. Yes. And now minus 1 become plus 1, and then sine of n plus 1 theta. Yes. And gamma of 2 is just 1 divided by n plus 1 whole square. Now if we shift the base from n to n plus 1, we have sum from n equals to 1 to infinity sine of n theta by n square, and we know that this sum is just the Clausen integral function CL2 of theta, which proves our claim. So we have really proved that this is also the integral representation for CL2 of theta. First of all, broken this down to the using Euler formula, done partial fractions, used geometric series, used gamma function, and got the answer. So this was it, and this will be helpful in the upcoming videos to find some special values of Clausen integral function, just like Clausen integral function for 2 pi by 3 or pi by 3, or the other values which aren't really obvious using the series. Let's say for theta equals 0 or pi by 2, its value is obvious from the series, but But 2 pi by 3 or pi by 3, it might not be obvious from this series. So we'll have to use this integral representation, and that will be helpful. So look forward to seeing you in the upcoming videos. So hope to see you there. And yeah, hope you have a great time. Thanks for watching.